Greetings, everyone, and welcome to this session, Advanced Statistics Techniques for Advanced Query Performance. About me, my name is Vern Rabe. I'm in the greater Portland, Oregon area. And two things I like to focus on here is that I've been working with a SQL Server since 1992. I had a small stint where I did some Oracle work, but almost all SQL Server since then. And I started with version 4.21a, which I doubt if any of you are familiar with it, but it crashed a lot. This is back before it was really enterprise ready. Still an amazing piece of software, but it's made so much progress over the years. And the other thing is that my first PC had a 10 megabyte hard drive, not gigabyte, megabyte. And that just, again, points out how old I am. So what we're going to cover today. We're going to start out by talking a little bit about the optimizer. I will assume you know somewhat about it, but it's always good to have a review, go over what it can do. Then we'll talk about the statistics a little bit. Again, I assume that you know somewhat about some things about statistics, but let's review them. Maybe touch on something you weren't familiar with or remind you of some aspects of it. And then we will have the meat of this whole presentation, some specific statistics solutions. That's to me, the real value. But you know, the foundation that I'm going to cover up front is important also. So an overview of the optimizer. So what does the optimizer do? When you submit a query, it's the optimizer's job to come up with a plan, a method, a step-by-step method to actually execute that plan. You'll hear people say a lot that it comes up with the best plan, and I very deliberately noted that in my slide deck here. It is not necessarily the best plan, and this is how it works. So when you submit a query, one of the first things that happens is a threshold is determined. What that threshold is an amount of work, maximum amount of work that should be necessary to satisfy that query, to execute a plan that satisfies that query. And then the optimizer starts kicking in, and it starts going through various plans. And each plan that it looks at, it estimates how much work would this plan take to satisfy the query. And by the way, every plan that it looks at will return the exact accurate results. This is not whether or not the results are accurate. They all will be accurate. It's just how it goes about getting them and whether or not the amount of work that is estimated, how much work it takes. If it finds a plan that takes estimated more work than the threshold, it sets that aside and grabs the next one. And it keeps doing that until it finds a plan where the estimated amount of work is less than the threshold. And then says, that's it, I'm not going to go any further. This is the plan we're going to use. And that's why it's referred to as a good enough plan. Now, one of the reasons that it does that is just time, because the optimizer is trying to find a balance between the time it takes to find a good plan and the time it takes to execute the plan. And this is a compromise for that. So if it keeps looking and looking and looking, it will actually time out, although it's not a timeout. If it looks at 500,000 plans and still hasn't found one that is the estimated amount of work is less than the threshold, it will stop right there and take the best one that it's found so far, which is not, quote, good enough, but it's not going to keep looking. It's not going to spend all day trying to find one that's less than the work. It's going to take the best one it's found, and that's going to be the plan. And that's a timeout. And that's something you want to avoid. There's the other possibility is that if it's a really small query, the optimizer said, it's going to be just so fast to look at all of the plans because there's only 100 of them. Just go ahead and look at all 100 and take the best one. So in other words, it might find a good enough plan, but still find a better one. In which case, it is the best plan. So how does it come up with those estimates of how much work will a given plan take? Well, cardinality is a major factor in that. What is cardinality? Cardinality is the estimated number of rows that is coming out of an operator. And that operator could be a table scan, an index seek, A join, like a merge join or hash match or nested loop, those are all operators. And the cardinality is the estimated number of rows coming out of that operator. The optimizer uses those cardinality estimates to determine how best to execute a plan. So for instance, if it gets, for instance, it's going to join two tables, and those two tables each of them have 10 million rows expected out of them, it's going to say, that's a hash match. I'm going to see what a hash match looks like with that, because it's a whole bunch of rows. On the other hand, if one of the tables has, say, 20 rows expected, and the other table has an appropriate index, then the optimizer might decide to look at a nested loop, which might be appropriate for that combination of cardinality. The bottom line is that cardinality is an absolute major factor in the optimizer's work in determining a plan and estimating work for a plan. And cardinality, by and large, is determined from statistics. If coming out of an index or a table or a column, those are the statistics. Once you do a join, the cardinality out of that join is a result of the prior two statistics. There's no statistics on a join. But coming out of tables and indexes, that comes from statistics. And so the cardinality estimator is the piece of software that says, here's statistics. And based on the predicate supplied in the query, this is the number of rows that I expect. This is the estimated cardinality. Taking the statistics and converting that to an estimated number of rows. It's very important to realize that the cardinality estimator was rewritten in SQL Server 2014. The prior version, which was created way back when with Sybase, it was in place for over 20 years. So it was a very good one, but it wasn't perfect. I'm sure the current one is not perfect, no such thing. But there was a few improvements made to the cardinality estimator starting in SQL Server 2014. Some notes about that. If you upgrade SQL Server from something prior to 2014 to 2014 and newer, you will be going from one cardinality estimator to another, and that can have some significant impact on the performance of your queries. What you will probably see is this. The majority of the queries won't change. They'll have the exact same plan. A relatively small but not insignificant number of queries will actually improve. The cardinality estimator came up with better estimates, came up with a slightly different plan, and the query got better. And then you'll have a very small number of outliers, those queries that even though overall the new cardinality estimator is good, it could result in a poor execution of some queries compared to the old estimator. So anytime that you upgrade from 2014, you need to be aware of that. And there's some well-documented processes how to go about that specific upgrade to take advantage or to consider the cardinality estimator changes that you're going to encounter. Overview of statistics. I usually don't like to read from my slide deck, but this is such a well-stated statement. Estimated summary information of the distribution of values in one or more columns. Key parts of that are, number one, and I really want to emphasize this, estimated. Statistics are not precise. In rare occasions on tiny tables they're precise, but the vast majority of times they're only estimated. Summary. The statistics histogram, which is the most significant, most important part, in my opinion, of the statistics, has 200 steps. It can only consider 200 different values that are in a given column. And if you have a table with millions and millions of rows, those 200 rows are an attempt to give you that summary of how the data is distributed. And the distribution is the key word there. One or more columns. You can have an index and you create your own statistics. Those can have more than one column, but most of the other ones, in fact, all of the other ones have a single column. When do you get statistics? Well, there's three cases. all indexes by default, or not by default, by definition, will have statistics on them. There is no choice on that. You can't create an index without statistics. And once created, you can't drop the statistic. The only way to get rid of it is to drop the index. By default, any column that you use in a predicate will get statistics on it. And what I mean by default is that you can turn that behavior off. Rarely do you want to. Usually you want it left on. But the way it works is this, is that someone submits a query to be executed and the optimizer looks at it. And there might be a predicate in there, something like where this column is greater than 5. The optimizer looks at that predicate and says, you know, if there were statistics on that column, I might be able to come up with a better plan. I could use those statistics in my considerations. So it stops right there and has statistics created on that column and then determines how to execute the query. It comes up with plans. By the way, that behavior also of having it calculated in the middle of the query before actually executing the query, that behavior can be changed. You can turn that off so that once it says, I wish I had statistics on this column, if it's deferred, the query will go ahead and get optimized. It'll come up with a plan. And then after that, then the statistics will be created. So any subsequent execution of the same or similar query can use those statistics. Again, by default, it will create the statistics, and by default, it will be done as prior to or part of the actual optimization of the query itself. Lastly, you can define your own statistics, and you can yes, no, I don't. When you define your own statistics, you can say, I want statistics on this column, or I want statistics on this column plus this column. And you can also say, I want statistics on this column, but only, and then have a predicate, only if that column is greater than 5, only if another column is greater than 5. You can put a filter on it to minimize the size of the statistics, so the number of columns that are considered in the not the number of columns, but the number of rows that are considered in that statistic included in it. There are 3 parts to the statistics: the header, density vector, and histogram. When you have a statistic on more than one column, only the lead column is represented in the histogram. The header is, as the name implies, header information. When was the statistic last updated? Things like that. Density vector covers having multiple columns in a statistic, the distribution of data amongst those 2 columns. And again, the histogram that's the important part to me. That's the most valuable part of the histogram. Reading statistics. There are a couple of ways to read statistics. I will go over both of them. The first one is the tried and true DBCC show statistics. That's been around since the beginning, I think. And you pass in 2 parameters to that. The first one is a fully qualified table name, followed by the statistics name. They're both names, neither one are IDs. And I've showed one of the options with histogram, because without an option, it returns multiple result sets, and I only typically want to see the histogram. The other, more recent and preferred, in my opinion, way to look at the statistics is using the Dynamic Management View DMDB Stats properties and or DMDB Stats histogram. And notice here that it passes in the ID of both the table name and of the statistics object. This Dynamic Management View became available in one of the versions of 2016, as I highlighted there. I have a little red dot here, and that's the note to myself that I have a demo to show. So let's go do the demo. And I'm using AdventureWorks 2016 on this one. And what I start out with here is this query. And this query does nothing more than identify the ID and the name of the statistic object that I'm looking for, and I specify the table name and the lead column name. So this will return any stats ID and name, where the first column is carrier tracking number, because that's what I'm going to query. So when I execute this, I can see the results. It is obviously ID number 7 and that lengthy system-generated name for the stats object. That indicates that it was system created because the table was queried, or that column was referenced in a query. So now that I have those, I can plug them into the two methods of reading the queries, the DBC show statistics and the DB stats histogram. And notice that I'm specifying the histogram for the DBCC show statistics, and I'm returning only the columns from the histogram dynamic management view to match up with the DBCC to show you the similarity. When I execute these, I will get two result sets, and let's go through those just a little bit. Some of the values, the range high key, that breaks all of the values in that column into ranges, into steps, up to 200 steps. The range rows column is the number of rows, these are all estimated, that are expected to be between the specified range high key and the previous one. So as an example, if I were to look at this one right here, this value of 91 plus says that there is an estimated 91 rows less than this value, but greater than that value, the previous value. And obviously the very first row doesn't have any before it, so it has a range row of 0. The equal rows, common sense, is an estimated number of rows that are equal to this value here. The average, or the distinct range rows are the estimated number of distinct values between those two, this one and the previous row, so between these two. And the average range rows is a calculation based on these other values. I want to point something out. Notice here with the DBCC results, we have a null value in the range high key. There are values of null in that column. Nulls are not included in the dynamic management view. That is a bug. It was a bug, it's been fixed, but not in the version that I'm using. But it's good to point out because if you are not on SQL Server 2017 CU21 or newer, or on SQL Server 2019 CU7 or newer, and I'm not, I'm on 2019 but prior to CU7, then that bug still exists and you will not get nulls in the dynamic management view results. Okay, let's go into some specific statistics solutions. The first one has to do with correlated columns or correlated predicates, and a few definitions. A predicate is one of those lines, typically a single line, in a query that evaluates to true, false, or unknown, such as in a where clause or a join clause. So you could have where this column is greater than 5, that's a predicate. Joining two tables on this column is equal to this column, that is a predicate. Correlated predicates or correlated columns are when you have two columns where the value of one is somewhat influenced by the value of the other. A common example is city and state, if you're looking at the cities and states in the United States. So if you're given a city of Seattle, what are the chances that the state is California? Pretty slim. But what are the chances that the state is Washington? Pretty high. So those two columns are correlated. The optimizer, prior to 2014, would not consider columns to be correlated whatsoever, and it would calculate, come up with an estimated cardinality based on them being totally independent. Starting with 2014, there's an assumption of some degree of cardinality, of correlation, but not tightly correlated. It's an estimate. There's no way that the optimizer can know how much any two given columns are correlated. So it takes a guess trying to find a good middle ground between none and a lot. And because it's almost impossible to come up with a good estimate of correlation, there are often optimizer plan problems because it expects too much or expects not enough correlation between columns. One solution to that problem is a filtered statistic. And when you manually create a statistic yourself, or with an index, if you have a filtered index, you can limit that statistic to certain values based on the filter that you define. So in this example, start by cleaning up some of the stuff that we have. And this is the query that we're going to run. And we're going to go after the sales order detail and sales order header table. And I have two predicates. One of them says I want to look for product ID 921. And the other one is where the carrier tracking number is null. And so because we have two predicates, the question comes up, how much are they correlated? And again, the optimizer assumes a small degree of correlation and comes up with a plan, a cardinality estimate, and therefore a plan accordingly. So when we execute this and take a look at the actual execution plan, we'll notice a couple of things. First of all, I want to point out, if you have a newer version of SQL Server Management Studio, which I hardly recommend, that the actual versus the estimated number of rows are right here, easy to see. You don't have to hover over one of these data lines to see the actual versus estimated. They're immediately available, so that's really handy. And it also immediately gives you that percentage, so you can hone in on those percentages and look for anything that's not close to 100%, and that's probably or possibly a problem. So in this case, coming out of the sales order detail table, it expected 1,430 rows and got 0. And because of that, because of expecting the 1430, it decided to do a merge join, which is a totally legitimate plan based on getting 1430 rows. But it may not be a good plan with 0 rows. So this is due to the fact that these two columns are correlated a lot more than the optimizer estimated. And let's just take a look at the correlation. And as I noted here, 47% of all rows for any of them, for any product ID have a null carrier tracking, but none of the product ID 921 have a null tracking number. So that means that they're tightly or somewhat tightly correlated. And just to show you, there is the two percentages, 47% and 0%. So product ID 921 doesn't follow the standard distribution of nulls for carrier tracking number, which is the average for all of the product IDs, and that's what makes them correlated. So let's create a statistic where the carrier tracking number is null. So then we eliminate all of those ones that have a carrier tracking number, that don't have it, and we get a better idea, or the optimizer can have a better idea of the distribution for product ID 921. So let's execute that. And now we will re-execute the query. Same query as above. And when we look at the execution plan, first of all, you'll notice that it's not a merge join, it's a nested loop. And a note about nested loops. I see a lot of blog posts that get rid of this nested loop, it's a problem. Nested loops have their place. This is a great example. A nested loop is the right choice here. Don't think that nested loops are bad. Nested loops have their place, merge joins have their place, hash matches have their place. It's when it should be a hash match, for instance, and instead it's a nested loop, that's when you have a performance problem. So in this case, notice now it estimated one row because it had better statistics and it came up with a much more appropriate plan. Notice also here that this is a seek, whereas this is a scan. You can see by that icon. Okay, that's not the only way that you can fix correlated columns or correlated predicates. You can also create statistics that cover the two columns in question. I call it covering, although that's my term. And again, I have my red dot, so I have a demo. And then, again, I'm still using AdventureWorks 2016. And I'm going to turn on the actual, or the statistics IO. I'm going to conditionally delete something there. Okay, so in this query, I'm looking at a city of London, and a state province of 14, which is England, which is really a country. And as you might guess, those two are correlated. And I want to point out a few things. We're going to take a look at the page IO. Again, a page IO is typically, not always, but typically the biggest resource in a query. So if you can reduce the IO, reduce the number of pages that have to be read, you're going to speed up the query. Okay, so let's execute this and take a look at a few things about it. In messages, we have logical reads of 1300, of 346, and of 1220. So that's 25, 28, some 2,900 or so pages. To that, just under 3,000 pages had to be read to satisfy this query. And taking a look at the plan, here we have two nested loops. Look at it, return 434 rows and expected 43, which is a 1,009%. I mean, that's a flag right there. Anytime that I see a nested loop followed by a nested loop, not always, but sometimes that's an issue. But again, this is the key, that 1,009%. That's definitely a problem. So, and it is a problem because of the correlation. So this time, we're going to create a statistic object that has two columns in it, the city and the state province. And when you do this, when you have correlated columns like this, experiment. Sometimes having the state province first works better. Sometimes the city first works better. Sometimes based on the city and state, sometimes one might work better or the other, so create them both. Create a person city-state and a city-state person. In this case, the city followed by the state province works best. So I'm going to execute that to create the statistics. I'm going to now execute the exact same query. We'll start by looking at the IO. And let's see, 0, 0, here's 108. 346 and 46. So we're 3, 4, we're talking right about 500, and the other was almost 3,000. So that's a significant improvement in IO, which almost for sure is going to make it run faster. And when we look at the execution plan, notice instead of two nested loops, it's a merge, join, and hash match. So the optimizer, getting better estimates from the statistics, came up with a totally different plan. And notice how close our estimates are, 99%. That's darn good. 106 is great. I'll never worry about that. Okay. How about insufficient granularity in large tables? Remember that the histogram of statistics has a maximum of 200 steps. So the histogram can identify 200 different values in a given column and no more. If you have a huge table, a billion rows or hundreds of millions or even a million rows, 200 values can be pretty insignificant. This really comes into play when your data is skewed. If you have a table that increments evenly, 1, 2, 3, 4, 5, 6, then you have less of a problem with the larger tables and the insufficient granularity. But if you have a whole bunch of values at different points within the range of values, that's a skew, that can result in more problems. And again, filtered statistics can often be a solution. You can take sections of the range of values. If you have dates, you might create multiple filtered statistics for every month that's within the table. That'd be a lot of statistics, but remember, each statistic is one page, and it usually, but not always, is a quick maintenance. It maintains offline if you can. You can do it manually with a job at night if you don't have 24/7. In other words, statistics, unlike indexes, are much lower maintenance and much lower of an impact. So when we take a look at this, what do we have here? I'm using a utility database. I haven't mentioned that. Anytime that I work at a client, I encourage to create a standalone utility database for, as the name implies, utility things. And one of the things that I like to do is put a numbers table in there, which comes into play a lot. And I'm using that utility table to create a table and for this example. So I'm going to conditionally drop statistics if it doesn't exist. I'm going to show, before we started, I created a large table. And this is our sample table that we're going to use. And I called it large table, DBO large table. And I have two columns, an integer and a decimal 9-1, just to try and fill it up a little bit. I have 18 million rows in it, and here's a query just to show you that between these two values, 1 million even and 1,900,000. Let's see how many rows we have out of there, and let's take a look at the plan that we get when we execute it. I did skew the data deliberately. We have 9,000, almost 10,000 rows. And when we look at the plan, we have a nested loop, concatenation with a merge, and how do our percentages look? Our percentages look good until we get to here. That's a little bit off. So let's create statistics on this table where I'm specifying that range of values between 100 or 1 million and 1,900,000. That's just a filter. So now I'm going to, nothing else, just that. Now, let's see the exact same query. Take a look at the estimated versus actual. And notice how much closer these are now. They're 116, which is quite good. These are right at 100%. So there I improved the query a lot. That query wasn't terribly performing, but it will perform ever so slightly better this time. And if the results went on to feed another join, that's where things continue to amplify and discrepancies like this get worse and worse. So filtered statistics can take care of some large table granularity issues. How about bad statistics? So when you query a table, when you reference a column, if there are no statistics on that column and the optimizer thinks that statistics might be helpful, the optimizer will request statistics be created on the spot for that column. That's the _WA statistics. That algorithm, to fill it up, it uses an algorithm to sample through the table, and then come up with the histogram. That algorithm is not perfect. It can't see the skews without doing a complete table scan, and it doesn't. It scans the sample size. And as a result, every once in a while, you get some statistics that are simply bad. By nature, they're bad. And this is one that I happened to encounter in the wild. I didn't have to create this. This is in AdventureWorks 2016. And I'm going to execute this query. From sales order header joining sales order detail, where the order quantity is equal to 15, okay? So I'm going to execute that, and I'm going to look at the row count coming out of the detail table. And also note the plan. Notice that it's a merge join. Okay, here is the header, here's the detail. It estimated 11,000 rows, but got 119. So that's way off. And because of that, it came up with this merge join. And had it had 11,000 rows, a merge join probably would have been an appropriate join operator. So let's take a look at the statistics. And again, I'm going to use this query that identifies the ID and the name of the statistics that start with order quantity, because right up here, try it again, right up here is where I had a filter for the order quantity. So I'm guessing that that's the column in question. Let's take a look at what we get. And we're going to use dynamic management view. So there it is. It's a stats ID 6. So here is the dynamic management view, and I've plugged in a value of 6. And again, the ID for the table that is in. Execute that, and let's take a look at the statistics. Notice that there's not a lot of distinct values, obviously, in the table, and that's why they're integers. But look at this here, right? Look at this range of rows right in here. So this one says for the value of 14, there's nothing between 13 and 14. Of course, these are integers, there aren't any. And it estimates that there are 234 with a value of 14. This is the one that's curious right here. This says that there are 11,000. Does that number look familiar? That's the estimate, the cardinality estimate in that plan, that are greater than 14, less than 16. That would be 15. These are integers. That seems wrong to me. And by the way, I did not create these statistics. These were created automatically by querying the table. So let's take a look at the actual data between those two values, including 14 and 16, and just confirm that we don't have 11,000 rows in there. And sure enough, there's that 119, but the statistics thought that there was going to be 11,000. So one solution here is to not use the standard default sample size, but specify with full scan. And I'm going to update the statistics. And in order to update, I have to have the name, and there's the name that we got from that query above. So I'm going to update it with full scan. Hopefully I get better statistics. So let's take a look at the statistics and see if they're better. And sure enough, now it shows the actual 119 for 15. So let's requery this table, see if we get, that's the same query as above, see if we get better estimates and therefore a better plan. Let's go to the actual execution plan. Notice, first of all, we have a nested loop. Where's the detail? Here's the detail, and now the estimate is 119 out of 119, much better. Here's another example where the nested loop is a better choice. So this one was only because the default sample size came up with bad results. And to point out, I want to point out that if I execute this again without the full scan, I'm just going to update the statistics. And let's take a look at the statistics again. You see that? It's a different number. 2019, by the way, does some wonderful things behind the scenes, and that's why it's an improved number. But it's wrong. It's still wrong. So what's the solution? Well, as you saw, I updated the statistics with full scan, and that solved the problem. But that solution was only temporary. Only temporary because as data changes in that table, though a threshold will get reached, and the statistics will automatically, by default, automatically be updated again. And that automatic update, by default, will go back to that default sample size. And guess what? Your problem will come back again. Couple of solutions. If you are prior to SQL Server 2016 SP1 Cumulative Update 4, what you need to do is turn off the automatic updating of that one column and create an agent job as frequent as you want, as is appropriate, to update the statistics using a full scan or some larger percentage. Very nice addition to SQL Server 2016 SP1 Cumulative Update 4 is a persist sample percent. So if I update statistics and I include the parameter persist sample percent, that is a flag that is stuck with that statistics. And the next time an automatic update of the statistics takes place, it will use that percentage that I used when I executed it. And let me show you how that works. We're going to be still in 2016. I'm going to update this is the persist sample percent, part of the update statistics option. And by specifying that, anytime I execute or anytime those statistics are automatically updated, it will get the full scan. And pre-SQL Server 2016, show you a couple of things. First of all, SP Autostats, a system stored procedure. When I specify it with just a table name, it will return a value of all the statistics for that table and their status. So let's execute that and take a look at the results. There are all of our statistics, and there's a key thing that I want to point out, the autostats. This says that every single one of these statistics are configured to automatically update anytime the threshold is reached. So one of these, I'm not sure which one it is the one in question. Let's see if I can BE57. It is column 4, which is this guy right there. So this guy, I want to turn off the auto stats. This is prior to SQL Server 2016. I don't want it to automatically update because when it does, it'll get those bad stats again. So what you can do is you can turn off column or stats by stats with this syntax by turning it off. That one statistic object will not get updated automatically, but the other ones will. So let's execute that. That's turning it off and then taking a look again at the end result. And in this case, now you'll see that that one statistic object is turned off. It will not get updated. So that's what you need to do if you're prior to 2016. calculations or computed columns. So a computed column, well, let's talk about calculations. Let's say you have a query that you're querying a table, and you have columns in that table that are the number of orders and the price per order. So in fact, let's take a look at our query. So I'm going to use, in this case, I'm using AdventureWorks DW 2016. Clean up anything. And I might have a sales order. I'm going to be adding a sales total computed column to the table, but that's part of the solution. But what I want to point out here is a query where I include a calculation as a predicate. I want the order quantity times the unit price. And I only want to return stuff from that table where in other words, the quantity times the price would be the total price, is greater than 35,000. This is a fact internet sales and the dim sales territory. So when I execute this, and I have actual execution plan turned on, take a look at the actual execution plan. Notice that it's a hash match. And notice this percentage coming out of the fact internet sales. It only got 37 rows, but it estimated 18,000. When the optimizer looks at that and it says, here's a predicate, I'm going to multiply two columns together. The algorithm to come up with an estimate there is just no way for it to know what those values are. So it takes a wild guess. And its guess ended up with this cardinality estimate of 18,000. It's a total guess. We want to give the optimizer as much information as we can. We want to help it. So one way to help it, did I execute that already? If I did, we're going to get an error when I execute it again. But I am going to add a column, and it's going to be a computed column. Notice that I'm not persisting it. I am not persisting. That will take up disk space. It'll make the table larger. This is a calculation. It is metadata only, meaning that right there it has a pretty small footprint. So I'm going to execute that. Yeah, I did execute it before. So we have this column now. And now, when I execute this exact same query, notice that I am not specifying the new column, I'm not specifying this sales total column. I'm specifying that same calculation that I did up above, but because that calculation matches the definition of that computed column, it will say, wait a second, I've got a computed column here. Let's put some statistics on that computed column. Remember, statistics are small. And then use those statistics to come up with an idea. So when I execute this, now let's take a look at the execution plan. Now we have a nested loop. Look at that, 37 estimated, 37 actual. And in fact, if I take a look at the properties here, we can go take a look at the stats that were used. One of these, and it's not that one. I believe it's that one. That is the statistics for that computed column that I just created. Okay? Ascending key. In my opinion, the ascending key may be the most prevalent performance issue caused by statistics. And here's the explanation. If you think about the histogram, the 200 steps, there is a first step and there is a last step. And as you saw when I showed you the histogram, the estimated number of rows prior to the first step is 0. There's nothing before it. And the same is true with the last step. The estimated number of rows after it is 0. So anytime that you have a predicate that says, I want just the columns or the rows where this column is equal to a value that is outside that range, less than the first one or greater than the last one, the optimizer says, well, I can never estimate 0. I have to estimate 1, but that's what it estimates, 1. But if there are a bunch of rows outside of that range, it's going to estimate 1, depending on which version of SQL Server you have. What kind of situations can result in a lot of rows being inserted into a table outside of the existing range of the histogram? Well, there's a few. One common is an identity column. And let's say we have an identity column on a table and we get statistics on it, and those statistics are updated, and it will have as the largest value, no more than the largest value that's actually in the table. But then as you start to insert rows, every single row that goes in is greater than the largest one in the table, even though the histogram isn't aware of it. Another example is something like a lot of date columns, a sales date, input date. Usually those are an ever-increasing value, which typically means they can be outside of the range of the histogram. That can cause some performance problems, and we're going to use AdventureWorks 2016, and let's take a look at this histogram, sales order detail number 5, and that is the modified date. Let's execute that. And when we look at that, I have it in descending order so that the highest value that the histogram has for the modified date is this 2014-630. Okay, that's the largest value that's in the table. So I'm going to insert a whole bunch of rows. I have to start by inserting into the sales order header because of foreign key relationship. I need those, and then I'm going to insert into detail. I want to point out one thing. If you're not aware, a go followed by a number simply executes that batch that multiple number of times, and I want to execute it twice. I will execute that. Now we'll have several thousand rows in the sales order detail table, all of which will have that date value outside, the modified date, outside of the value in the histogram, the highest value. So it is now completed. So I very specifically determine how many rows to insert to not hit the threshold to trigger an automatic update of the statistics. Had I reached it, this query right here would result in the statistics being updated. And I'm going to execute it just to make sure. And it doesn't matter the results. We're just looking at what the statistics look like. And now we're going to take a look at those statistics again. And when I execute this, notice that we still have that same maximum value. I did not trigger updating of the statistics. But in fact, with this query, you'll see how many rows are in the table where the modified data is greater than that greatest value. And you'll see that there's like 4,000 of them, because those are the 4,000 rows that I inserted into the detail table. Okay, we have two situations. We have compatibility level 110 and higher at 2014. So if I use compatibility level 110, that's 2012 and earlier, it will assume that there's only one row above that value. I will put us into that mode. I will turn on the actual execution, statistics IO on, and I'm going to execute this query. And it's just a join with a modified date. Here's my predicate based on the modified date. And notice that this is greater than the greatest one in the histogram, but it is less than all of those ones that I entered. So when I execute this, a couple of things to point out. First of all, the I/O. We have over 13,000 pages had to be read to satisfy the query. And the execution plan is not a very good estimate. It estimated 1 and got 4,000. And that's exactly what I said, that if you are prior to 2012 or prior, and you have any values outside of the range of the histogram, the optimizer will estimate one row. But the cardinality estimator was rewritten in 2014, so it's going to improve it. So I'm going to change the compatibility level to 150, which is the current. And we're going to execute the same query again. And when we look at the messages, logical reads 2,400 instead of multiple thousand. And when we look at the execution plan, notice that we have better statistics. We estimated 1,200 and we had an actual of 4,000. The algorithm after 2014, the cardinality estimator rewritten, is that for every row that is changed in the table, it will assume that 30% are outside of the range. And so that's where it came up with the 1,200, that's 30%. So notice that we have a merge join, better estimates all the way around. Still not great, but better. So one last thing to do, we're going to update the statistics with full scan, or not with full scan. I commented that out. We're just going to update the statistics. Now we'll get the newer values. We're going to take a look at the dynamic management view, the histogram, see what it looks like. And again, I'm sorting in reverse order, so the largest values are here. And sure enough, remember I had 2 goes. They're 2 different executions of the batch, so I got 2 different times. And there are the rows. And now when we look at estimated versus actual, I don't want to see that. I want to take a look at estimated versus actual. And notice how close they are now. We still have a merge join, but the numbers are a lot closer. Quite comfortable with that. So if you are have any of these tables, I hardly recommend you look for cases where there's a lot of rows outside of the maximum range or the range of histogram, and it's a common situation. And the solution is to periodically update the statistics. You might do it once a night. I've got a client where actually more than one client, where we put the statistics update in the stored procedure that actually loads data into the table, so it's extremely current. Okay, summary of what we covered today. We went over a review of the optimizer in statistics, and we had some very specific statistic solutions using statistics in not so common ways to solve problems. In those solutions, covering statistics and filtered statistics are 2 of the main solutions that we used. And another is just adding a computed column and let SQL Server create statistics on it to satisfy some queries that you have. So I want to thank you very much, and we are now here for questions.